So I am Yeoul from Azu University. So catalyst world may be divided by two parties, homogeneous parties and heterogeneous parties. I think the homogeneous parties is to homogeneous parties what the Roman Catholic Church is to Protestant Church. So I think almost all audience and including organizer belong to heterogeneous parties. I am an alien, come from homogeneous parties, and I would like to great thanks for inviting an alien. And I think even though we have the same goal, we read the same Bible, so we have had very little interactions. So in that regard, I would like to great thanks to organizer. Now, my first topic is catalyst development for carbon dioxide epoxide copolymerizations. We can convert carbon dioxide to valuable polymer by copolymerization with some epoxide like this. It may be a true breakthrough in polymer technology in 21st century. So ethylene oxide copolymer is 50% weight carbon dioxide and propylene oxide copolymer is 44 weight% carbon dioxide. So almost all the polymers used in our daily life comes from totally petroleum. So this polymer shows low petroleum dependency. The polymer shows some biodegradability. It burns cleanly without emitting any toxic materials with almost invisible flame like this. Almost all the polymers burns like this with emitting or loss of the toxic materials, which causes some problem in disposal and a sudden death when fire. Because it contains polar group, it shows good adhesiveness and it displays very good barrier property for both oxygen and water. The first catalyst was developed, introduced 40 years ago, long time ago. It was a heterogeneous catalyst prepared by mixing dimethyl zinc and water in 1-to-1 ratio. It is not soluble, so it is the heterogeneous catalyst. The first catalyst shows very low catalytic activity. The heterogeneous catalyst has been significantly improved, and the most highly active catalyst is in the literature is the zinc, the glutamate complex. So with 1 gram of catalyst, we can make Professor Lee, Pohang University, can make 64 gram of polymer by running 40 hours. This catalytic performance is not sufficient when we consider commercialization. So lots of homogeneous catalyst also has been introduced, and the catalytic activity in terms of the activity and molecular weight was not satisfactory. The best catalyst when I got involved in this project was the binary system composed of silane cobalt complex and quaternary ammonium salt. This silane cobalt complex was introduced by Professor Kos in Korea University. Very soon later, Professor Lu in Dalian University reported that addition of 1 equivalent of quaternary ammonium salt improved the catalytic activity almost 10 times. So plausible, the propagation mechanism is like this. Cobalt center acts as a Lewis acid activating the coordinated epoxide, while the carbonate anion, which is derived from the anion of the quaternary ammonium, attack the activated epoxide. And under this, the propagation mechanism, so we have some problem. So rate of polymerization should be second order kinetics. So under this situation, it works only at a high catalyst loading. When we added a very small amount of catalyst, there is a little chance for the two components to meet each other. So the catalytic activity was realized at a high catalyst loading. So epoxide catalyst ratio below 2000. So under this condition, the highest attainable turnover number is limited by this number, so we cannot get a high turnover number up to 100,000 or something like that under this condition. And this polymerization shows the living character. The molecular weight is governed by the attained turnover number. Due to the low turnover number, the low molecular weight polymer is obtained, hampering to find some applications. And under this, the propagation mechanism, delta S delta should be negative, and the polymerization reaction is unfavorable at a high temperature. The polymerization activity was realized below 50 degrees. All the commercial process, the producing polymer, is run at a high temperature. So the polymerization reaction is the exothermic reaction. So in order to remove heat over polymerization, we have to run the polymerization at a high temperature. And in bulk and solution polymerization, so we got a very thick viscous polymerization solution, and the productivity per unit volume is governed by the viscosity. So at high temperature, the viscosity is typically reduced, so we can make much polymers using the same size reactor. So best catalytic performance obtained by the binary system is like this. Using these catalytic numbers, we can publish in a very highly reputed journal, but we cannot go into the commercial process, still very low values. So I devised some strategy to overcome the disadvantage. So problem is that the very low chance to meet each other of both components at a especially high temperature, and when we added a very small amount of a catalyst. So in order to plug this kind of dissociation, the concept is very simple, connecting the two components. By connecting two components situated in proximity, you will have a high temperature and the monomer catalyst ratio. So I was able to prepare the silane cobalt complex tested by quaternary ammonium salt by simple organic synthesis. And my concept, so I can see my concept works. So by connecting the two components using the flexible linker, so it shows the activity very low catalyst concentration, epoxide catalyst ratio 25,000 to 1. And at this condition, by obtaining the thick viscous polymer solution, we will increase the turnover number almost 10 times. Because of the high turnover number, we can obtain the high molecular weight polymer. Turnover frequency was also increased doubly. It shows the activity at a high temperature of 80 degrees without formation of the formation of a negligible amount of side products. This catalyst, the only produce is the cyclic carbonate at a high temperature. Because my concept works, I prepared the derivatives especially by bearing some steric hindrance at this position or bearing the number of quaternary ammonium salt. And then, to my happiness, this catalyst having very small metal substituent here and for quaternary ammonium salt shows fantastic catalytic performance. It works at a very low catalytic loading, epoxide catalyst ratio 100,000. At this condition, by getting the full conversion, we can get the turnover number more than 20,000 due to high turnover number, high molecular weight polymer obtained. And interestingly, turnover frequency was also dramatically improved, 15 times improved. And it works at a high temperature of 80 degrees with very high selectivity. So with 500 milliliter reactor, we can make this kind of thick viscous polymerization by adding 100 milligram of catalyst, so using 300 milliliter propylene oxide by running just 1 hour at a temperature of 75 degrees C. So we can make 1 kilogram of polymer with 1 gram of catalyst just by running 1 hour. So even though I have developed a very efficient catalyst, I have still one problem. So isolated polymer is yellowish like this because it contains cobalt residue. And cobalt is the transition metal, it is toxic, so we cannot use a resin containing a toxic cobalt residue. So I have devised the catalyst separation strategy. We can, after polymerization, the solution is yellowish like this because it contains the homogeneous the cobalt catalyst. When the polymer solution is passed through just the short pad of silica gel, the catalyst can be served on the surface of the catalyst like this very efficiently, and the polymer solution liberated with colorless solution. And after the polymerization, all the counter anions of the quaternary ammonia become the carbonate anion or alkoxide anion appended at the end of the polymer chain, and during the filtration, the protonation occurs from the proton on the surface of the silica surface, liberating polymer into the solution phase, while the cobalt complex can be served on the silica surface. So polymerization is carried out at the homogeneous phase, and catalyst is separated out by some heterogenized method. So the isolated polymer contains negligible amount of catalyst. So final objective is the catalyst recovery from the chemistry of the cobalt complex. When this silica cobalt composite is dispersed on the just methanol, nothing was extractable. But when I added the sodium tetrafluoroborate, anion exchange reaction between this surface silox anion and the tetrafluoroborate occurs, liberating cobalt complex into solution phase. And the extracted cobalt complex can be converted to the active catalyst by simple treatment, and we can also reuse the silica gel by just washing with the acid. So, based on the research activity, I patented and I licensed out the intellectual property to SK Innovation several years ago. So, and in Korea there is no tax is exempted for this kind of royal income. So Korea is a very wonderful country for scientists. And SK is a very wonderful partner. SK constructed this building, pilot plant, within 1 year by investment of $10 million. And this is the first continuous process to produce the carbon dioxide polymer. And this pellet is resin, the resin produced in this pilot, and this article is made with this pellet. And now more than 50 researchers are involved in commercialization of this attractive resin. And this slide was provided by SK, and the target application of the polymer is the replacement of flexible PVC and some coating adhesive and packaging film and sheets. So several months ago, this polymer was broadcasted in YTN News, and he is Chae-Tae-won, the owner of SK. He is the CEO, 부자용, CEO in SK Innovation. He is the president of Colombia. He visited SK, the Ulsan complex. And this wallet is made with the carbon dioxide resin. This is the SK Innovation advertisement. We can see this advertisement in newspaper. And one of the mark initiated by myself, so I'm very happy when I look at this advertisement. So I would like to briefly introduce another successful story, catalyst development for ethylene α-Olefin Copolymerization. Huge amount of polyethylene and polypropylene is now being produced by Ziegler catalyst. Ziegler catalyst is also homogeneous heterogeneous catalyst prepared by mixing triethyl aluminum and titanium tetrachloride. And in the 1970s, the homogeneous Ziegler catalyst, which is called metaloxide catalyst, was introduced, and the merit of the homogeneous Ziegler catalyst is that we can control the polymer chain structure there is molecular weight distribution, hormone incorporation, and practiced by modulating the ligand structure. And in this report, I think more than 10% of polyethylene is now being produced by the homogeneous metallocene catalyst. This is called Dow CDC. Among the homogeneous ziegler catalyst, this was reported the best developed by in the 1990s, early 1990s in the Dow, and it displayed very high activity, high hormone incorporation, high molecular weight, and good thermal stability. So I designed the new catalyst, especially replaced this dimethylsilicate group with orthophenylene groups. So when I designed this catalyst, nobody had reported this kind of catalyst. So I designed the synthetic route for the targeted complex. This reaction is, the key step is the Suzuki coupling reaction of this boronic acid and 2-bromine. Suzuki won the Nobel Prize last year on the discovery of these nice coupling reactions. The next step is not easy, but the many chemists have developed converting the cyclopentane into the titanium complexes. Because this boronic acid was unknown at the time, so I developed a synthetic route for the targeted boronic acid by simply without chromatographic several tens of gram scale. Using the route, I was able to prepare the bunch of catalysts, more than 40, the new complexes, and I screened in the ethylene α-Olefin Copolymerizations, and this compound, this catalyst was turned out to be the best. And the catalytic performance in terms of α-Olefin incorporation, activity, thermal stability, molecular weight was not behind than the dose compared with the dose of the CGC. But when we consider commercialization, it has a problem. So we should be able to prepare the catalyst kilogram scale with the price of 10, I think the $1,000 per kilogram. But in order to prepare this compound, 8 steps are required, so we cannot make a successful story using this route. So conceptually, if we have this aryl lithium compound, ortho-lithiated aryl lithium compound, the nucleophilic attack and the acid work provide the desired ligand just one step conceptually. So I have focused on generation of this lithium compound. So when I added, this is very cheap starting material, one equivalent of this lithium, lithiation occur on this the amine proton because this proton is more acid. And when I added one equivalent of this lithium, nothing has happened. So because I have carbon dioxide in my lab, I have the thought addition of the carbon dioxide convert this lithium amide to lithium carbamate, and this lithium carbamate acts as the directing group in ortho-lithiation reactions, liberating the targeted ortho-lithiated compound. This is a very fundamental chemistry developed by myself to achieve the target complex, and this lithium carbamate group is easily removed to convert the secondary amine group, just the acid workup procedure. So using the chemistry, the fundamental chemistry developed by myself, I was able to prepare the targeted ligand in kilogram scale, just one step. And then I was able to prepare newly 22 complexes based on the synthetic scheme. Among the 22 complexes, this catalyst shows best catalytic performance. And the catalytic performance of my catalyst shows the better activity and better the α-Olefin incorporation, and it provides a higher molecular weight polymers. So this catalyst, in my polymerization condition, was better than the Dow CGC. And based on this research activity, LG started business in 2008, and they are doing very good business. The production capacity still increased, and I heard that in this year, LG was planning on producing 60,000 ton of polymer. The sales unit is around the $0.1 billion. Upon this successful story, LG has to take care of me, but LG did not contact me at all initially, because this work was carried out by some government fund between the collaboration. So eventually, I was able to prepare this compound in order to, just with an aim to publish one paper. So I was under the very high stress to publish many papers. I was very familiar with the synthesis of catalyst. And this catalyst shows some advantageous performance than the catalyst I have provided to previous LG, higher thermal stability, high molecular weight. And the preparation of this compound is a little bit simpler, and the yield is higher. And when I look at the LG, the patent carefully, they have claimed just alkyl, aryl, alkenyl, alkyl substituted cyclopentadiene complex. This is not the alkyl, aryl, or alkyl substituted cyclopentadiene. So it is out of the boundary of the LG patent, and then I got a patent. And we have 7 polyethylene producers. I have sent 1 gram of sample each companies, and 3 companies were very eager to buy my catalyst, because LG demonstrated successful story on the similar type of catalyst, and eventually I sold the catalyst to Honam Petrochemical this year with 6억 won. And I heard that Honam is very happy on buying this catalyst, and Honam is now constructing pilot plant to commercialize this catalyst. I would like to give thanks to my former and present students, especially red one is carbon dioxide polymer, the workers, and the blue one is the α-Olefin polymerization catalyst. Thank you for your attention.